Yep. Section 5, Digital Electronic Circuits. Chapter 32, Binary Number System. After completing this chapter, you, the student, are going to be able to describe the binary number system, identify the place value for each bit in a binary number, convert binary numbers to decimal numbers, convert decimal numbers to binary numbers, convert decimal numbers to 8421 BCD code, and convert 8421 BCD code numbers to decimal numbers. First things first, why binary? In an attempt to use circuits to solve complex problems, what they wanted to do is simplify the circuitry. And in simplifying the circuitry, they wanted to basically break everything down into two different conditions, or two different states. And that's a state of either being on or a state of being off. A state of either being a 1 or a state of being a 0. And the early advancement of digital technology was to perform repetitive functions accurately, over and over and over again. And this is really how digital was developed, and this is why the binary number system was initially used. And the binary number system, binary communication, really still is a strong form of communication outside of digital electronics. I mean, if you are going down a hill, down the bottom of the hill here, and you see a red light that is flashing on and off, on and off, on and off, what does that tell you? Do you all have your driver's licenses? If you have a red light that's pulsating on and off, what does that tell you? Stop. If it's a yellow light and it's pulsating on and off, what does it tell you? If it's a constant yellow light, what does that tell you? The caution, proceed with caution. So, construction zone, to grab your attention. So we use binary form of communication. What is it, the midnight ride of Paul Revere there? Remember, 1 if by land, 2 if by sea? It was a form of binary communication. So in binary you can communicate some very simple things. If you use a lot of binary, a lot of ones and zeros, you can transmit some really complex things. And that's exactly how the computer that I'm using tonight to put on this presentation works. You've got trillions and trillions and trillions and trillions and trillions of ones and zeros that just make up the ability to put on this PowerPoint presentation. But the one thing you have to understand is that all digital electronics boil back down to binary. So that's where we're starting tonight. You have to understand binary before you can understand the more complex digital systems. Binary numbers, a binary system, is a base 2 system. So it's got two different states, either on or off. It contains 2 digits, and those 2 digits are either a 0 or a 1. The position of the 0 or the 1 in the number indicates its value within the number. The place value of the digits in a binary number increase by powers of 2. So you've got 1s, 2s, 4, 8, 16, 32, 64. Does that make sense? All based on powers of 2. Our existing numbering system, base 10, increases by powers of 10. Your ones column, tens, hundreds, thousands, 10,000s, 100,000s. Does that make sense? The table here shows us the binary number system. Of course, the decimal number 0 equals 0, 0, 0, 0, 0. Let's focus our attention here to our least significant digit. Our least significant digit. The number of combinations that least significant digit could possibly be are 2 different conditions. It could either be a 0 or it could be a 1. This is a 0, which signifies the number is 0. This signifies the number is 1, which correlates to the decimal number 1. When I increment my value here to 1, 0, this is 1 in the 2's column, 0 in the 1's column. 2 plus 0 is equal to the number 2. 1 in the 2's column and 1 in the 1's column is 2 plus 1 is equal to 3. Let's go down here to a number that's a little bit more complex. 1, 0, 0, 1, 1. I have 1 in the 16's column. 16 plus 1 in the 2's column. 16 plus 2 is 18. Plus 1 in the 1's column makes the number 19. 1, 0, 0, 1, 1 is equal to the number 19 decimal. Does that make sense to you? And then this number just keeps going and going. 1, 2, 4, 8, 16, 32, 64, 128, 256, 512, 1024. Me rattling off those numbers, do any of those numbers sound kind of familiar to any of you? Where have you heard those numbers before? Yeah. Absolutely. Anything to do with memory, anything to do with computers, anything to do with computer digital configurations, they're all based on that because computers are all binary. And it's exactly how the progression developed. I remember the original Sound Blaster board back in the early 1990s was an 8-bit board. And then they went to a 16-bit board. You went from 8 to 16, from 16 to 34 to 62. 64. I say 62, 64. 128. These were all standard binary progressions. That's because that's how the machines, what drives the architecture of the machines. Make sense? Any questions on this? One of the big codes, there's a number of different codes that you're going to learn about later on when you get to Peter's class, and Peter's going to really hit you a lot more with digital. This, again, is designed to be an introductory class. One of the very, very important codes that we use is called the BCD code. BCD. BCD stands for Binary Coded Decimal. Binary Coded Decimal. This is taking a decimal number and coding it with a binary number. Binary Coded Decimal. What is the highest number that you could count to in decimal with ones place? 9. Very good. So the highest number that BCD will go to is the number 9. So you will not have 10, you will not have 11, 12, 13, 14, 15, 16, 22, 48, 73. The highest number you will ever have in BCD is the number 9, because that's the highest tens place number that we count to. Once we get to 9, what happens? When we're counting up, we go to 10. 1, 2, 3, 4, 5, 6, 7, 8, 9. And then what do? The number 10 is actually us incrementing 1 to the tens place and 0 in the ones place. What's the number 11? 1 in the tens place, 1 in the ones place. 10 plus 1 is equal to 11. Does that make sense? That's how we count. You probably have never really thought about it before if you haven't studied digital, but that's how we count. Okay? So this BCD code is also known as 8421 code. It's a binary coded decimal, BCD, and it consists of 4 binary digits. Those 4 binary digits are the 8th place, the 4th place, the 2's place, and the 1's place. So the 8421 designation refers to the binary rate of weight of the 4 bits. 8, 4, 2, 1. If I actually used, and I put a 1 here, a 1 here, a 1 here, and a 1 here, so if I gave you the binary value of 1, 1, 1, 1, what would that number equal in decimal? 15. Will you ever see BCD code that represents the number 15? What about the number 14? What about 13? 12? 11? What about 10? BCD code 10? What about BCD code 9? Yeah. So let me actually go back a couple slides here, okay? This here could either be considered, what we're looking at here in this entire table is what we call straight binary. This is straight binary. It's just a binary progression. We can keep counting here by just keep adding places. Are you with me? But these numbers here, all the way through this number here, 1001 is the highest value BCD code that you will ever see. Because as soon as we go from 1001 and we increment that one more, it's now the number 10. And the 10 is actually 0 in the 1's place, 1 in the 10's place. It's not pure BCD. So in actuality, if I wanted to represent the number 10 in BCD, does anybody have any ideas how I might do that? How many bits would it actually take for me to represent the number 10 in BCD? It would take 8 binary numbers for me to give the number 10. And what would those numbers be? 1, 2, 3, 4, 5, 6, 7, 8. What would they be? 0, 0, 0, 1. So BCD, this here is equal to, in decimal, 0. This number here in decimal is equal to 1. So it would actually take us 8 bits. 2 groups of BCDs to get to the number 10. Is everybody with me with that? Make sense? Okay. In summary, the binary number system is the simplest number system. It contains 2 digits, 0 and 1, used to represent data for digital and computer systems. Binary data, represented by binary digits called bits. A bit is derived from the term binary digit. Bit, B-I-T, binary digit. The place value of each higher digit's position in the binary number system is increased by powers of 2. The largest number that can be represented by a given number of places is base 2, 2 to the nth power minus 1, where n represents the number of bits. The value of a binary digit can be determined by adding the product of each digit and its place value. Fractional numbers are represented by negative powers of 2. To convert from a decimal number to a binary number, we divide the decimal number by 2. Writing down the remainder after each division, the remainders taken in reverse order form the binary number. So this is how we're going to add in binary. Okay, your book is loaded with examples. 8421 code is a binary coded decimal code used to represent the digits 0 through 9. The advantage of the BCD code is ease of converting between decimal and binary forms of a number. Why are we so hung up on BCD code? And what kind of number system do we rely on? Decimal. Everything we do. This is the amazing thing about it. I mean, I don't want to go off on a tangent here or anything, but I do a lot of travel. I've been to a lot of different countries. They speak a lot of different languages. They have a lot of different customs. But you know what? Wherever I've gone in the world, guess what? They use base 10. Maybe it has something to do with us having 10 toes and fingers. I suspect that that's probably the origin of it, counting on your fingers and counting on your toes. But we all use universally a base 10 numbering system, even though our languages are so different. So the computer interface, interfacing man with the machine, we've got to use this BCD code. Even your digital alarm clock, when you set your alarm clock to get you up at 7:30 in the morning, right? That's 0730. It's a decimal number that you're programming your clock to go off at. But it's really ones and zeros that are doing the work inside the clock. Does that make sense? Okay. One of the things that I want to show you now, let me get out of this PowerPoint presentation. By the way, all of your tests, all of your quizzes and your final exam, we're going to allow you to use the computer for all of these 120 quizzes and exams that you have left, with the exception of one. And I'll share that one with you in a minute. All the rest are open computer. When I say open computer, that doesn't mean research your answers on Google. Okay? It does mean that you could use the computer as a tool. Peter and I both want you to use the computer as a tool to solve these problems. I want you to do your homework longhand so you understand the process, but I want you to double check it with the computer so you see the capabilities of the computer. One of the things that's part of Windows, actually a lot of you may have this feature built into your scientific calculator, but even if you have it built into your scientific calculator, it's not as powerful as the tool that is built into Windows. Go to Start, Programs, Accessories, and go to the standard calculator that's available to you. Okay? If you open the calculator up and it looks like this, you've got to go to View and change it to Scientific. Okay? And this here is an incredible calculator for doing your digital homework on. Because let me show you something real quick. I could go into the decimal mode, which is what you normally want to do for addition and subtraction and balancing your checkbook. We could also put it in the binary mode. As soon as I went to the binary mode, look at my only keys that are active now are the 1 and the 0. All the other numbers are gone because they don't even have significance anymore. They don't even exist in the calculator. But one of the things that I want to show you here is the number of places that we could put into this calculator. Okay? So what I'm going to do right now is I'm going to go, this is the number 0. You all agree that this is the number 0 and the decimal equivalent is the number 0? Okay? This is the number 1. If I add another digit, what number am I looking at in binary right here? 3. Very good. 2 in the 2's column, 1 in the 1's column. 2 plus 1 is 3. How many of you say the answer is 3? Let me go right over here to decimal. I'll convert it into decimal. 1 in binary is equal to the number 3 in decimal. Okay? I could actually work this backwards too. If I want to know what is the number 57 equal to in binary, I plug in the decimal number and I go to binary. 111001 is the binary equivalent of the number 57. You with me? Mm-hmm. It's not gonna. You're gonna have to convert those manually. That is the one thing that this won't do. But you know what? You're not going to see that a whole lot in the real world. So just do it manually for your homework purposes. I'm not even going to go out of my way to ask you to do that on a quiz. I mean, you might give you one question or something like that, but I'm not going to go out of my way to ask you on a quiz or the final how to do that manually. This is the big thing I want you to all be able to do is convert a decimal number into a binary number back and forth. Now let me show you what's so cool about this calculator as opposed to your own scientific calculator, right? Let me clear this all out and let me start showing you the number of digits that we could plug in here, okay? 1, 2, 3, 4. This is a 4-bit system. 5, 6, 7, 8. This is an 8-bit system. You all remember the old 8-bit Sound Blaster board from the early 1990s, right? Your 486 computer. The decimal equivalent of that was 255 plus 1 Because 0 is another condition, isn't it? We don't use 0. I mean, you and I, when we count, we don't say 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. That's not how we count, but that is how machines count. So 255 plus 1 gives us 256. That 8-bit Sound Blaster board was capable of rendering 256 different tones. And that's what made it possible for speech patterns, recognizing speech patterns, playing music, MIDI, 256 it's pretty stout. That's a lot of different combinations. Okay? Let me convert that back to binary. So this is 8. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30. 31, 32, 33, 34, 35, 36, 37, 38, 39, 40, 41, 42, 43, 44, 45, 6, 7, 48, 49, 50. 51, 52, 53, 54, 55, 56, 57, 58, 59, 60, 61, 62, 63, 64. This is 64-bit processing here. This is pretty substantial. You know how many decimal combinations there are of 64-bit? It's a big number. That's a big number. John, I know you play around with the video and that kind of stuff in the PowerPoint and the paint, what do you call it there? What typical is how many bits are there in a high resolution digital photograph? Let's go with 12. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 4,095. 4,095 different combinations. Okay? I know for like digital photography, still photography, 24-bit is capable. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24. You got a high-end digital SLR. This is what it's capable of. 24-bit color processing. That's how many different colors you could get. I thought I had, with the Crayola crayons, how many were in that big freaking box. I thought that was a lot of colors. But no, this is how many colors are capable. Differences in each pixel. It's pretty substantial. One of the other things that I want to show you, although it's not part of this chapter per se, I do feel compelled that you need to understand this, is how many bits are there, how many bits capable are there with BCD? How many binary bits do we use for BCD? It's not a trick question. 4. Okay? 1, 2, 3, 4. How many combinations do we have possible to us using 4 bits? 15 plus the 1 is 16 different combinations. You with me? Okay? So, if we're using the 4 bits of BCD to communicate to us the decimal equivalent, how many places are we wasting? How many places are we not using? 10, 11, 12, 13, 14, 15, 16. Basically 7 combinations that we're not even using, but we're capable of. That's an incredible waste of computing horsepower, an incredible waste of digital horsepower. So, what the engineers came up with is a different numbering system that allows us to use 4 bits to represent the 16 different combinations. Does anybody know what that form of code is called? hexadecimal. Very good. Okay? Check this out. This is wild. Let's go back to binary here. Okay? 1, actually I'll go to hex. I'll go to hex, and we'll start counting. 1 plus 1 equals 2. Plus 1 equals, I'm counting up in hexadecimal. What comes after the number 2? 3. Plus 1 equals 4. Plus 1 equals, what did I do? I did something wrong. Plus 1, 3, oops. I know what I did. Plus 1, 2, plus 1, 4, plus 1, 4, plus 1, 5, plus 1, 6, plus 1, 7, plus 1, 8, plus 1, 9. What number comes after the number 9 in decimal? 10. We can't do 10 because that 10 is 1 in the tens place and a 0 in the ones place. Anybody have any idea what the next digit, the value is going to come after the number 9? Has nothing to do with numbers. Has everything to do with the alphabet. Exactly. So after the number 9 comes the number A. Plus 1 equals A. Plus 1 equals B. Plus 1 equals C. Plus 1 equals D. Plus 1 equals E. Plus 1 equals F. And F, right now, hexadecimal, is equal to the binary value 1111. This is the maximum value that you could count to in hexadecimal before you increment to the next place. So hexadecimal has 16 different possible combinations. BCD only had 10 different combinations, 0 through 9. Hexadecimal, 16. Does that make sense? Let me go back to hex. There's F. Now when I add 1 to F, what's going to happen in hexadecimal? What value is going to come after F? And don't say G. That's not the answer. If I have the value F, what's going to come after F if I increment my count here by 1? If I add 1 to F, what number comes next in hexadecimal?
1 would be 1A, or...
Close. Kinda. Not even close. You're so far off. I like the 1 part.
A1?
So use car dealership, A1 Autos. Think about it. When you get to the number 9 and then you count to the number 10, what happens? 0 through 9, the 1s goes back to 0, and you do what? You increment your count. So if I'm at the maximum value that I could count to here, in my first column, what's my next value going to be? 0. And then what's going to happen in my 1, 0. Very good. Plus 1 equals 1, 0. Not the number 10. And this is where you got to be careful, and this is where Peter and I are going to bust you guys. What's the number? 10. What's the number? No, it's not 10. This is 1, 0 in hex. 1, 0 in hex is different than number 10. You say the number's 10, I assume you're talking a decimal value. If you actually saw this number, 1, 0, I could even think what? I could think that this is a binary value. I could think this is the binary number 2. I could think that this is the decimal number 10, or I could think that this is the hexadecimal value 1, 0. That's what I want you to get out of this chapter. You can't take anything for granted anymore. You've got to look at it and be able to quantify what the value is and the significance in the machine. Make sense?
One thing I've seen with hexadecimal system used for is on the internet, on the web page, to tell the browser what color you want this, if you want the browser to display for like a table or something, or an element, you will put out a command that is a hexadecimal, that you'll use the hexadecimal system, through F or whatever, 0 through F, and you'll have, 4 place values or whatever for C, Y, and K. And so that kind of makes sense as to where this, now I understand where they actually, technically coming from.
Every digital system uses hex. For programming, for packets of information. If you're familiar with DirecTV, satellite TV, you know what they're doing? They are beaming down from their satellite packets of data, of digital data, for every channel that they offer, continuously. If you have a DirecTV receiver and you've got your satellite dish pointed towards their satellite, 33,000 miles out in space, you're listening to a stream of digital data, of packets of digital data that contain every channel they broadcast. And it's all getting into your box. What limits you from being able to watch all of those stations, and this includes pay-per-view, HBO East, HBO West, Showtime North, South, East, West, whatever, the Playboy channel and other channels we won't mention, right? All of those channels are coming into that dish in packets of data. And it's all in hexadecimal code. The only thing that precludes you from watching those channels is your receiver is not allowing you to tune to channel whatever that covers HBO. But the information is all inside your box. So all that you have to do, if you wanted to do this, and I don't encourage you to do this, it's not a good scene, is if you could tell your receiver to decrypt those packets of information, basically you could watch and have access to every channel that's broadcast simultaneously. And this was one of the things that was going on a few years ago with, if any of you heard, there was a lot of problems with access cards. There were a number of people that cracked the codes for unlocking the box. And once you unlock the box, all the channels are there. It's not like you got to go out of your way to descramble Showtime, and then you got to go out of your way to descramble HBO, and you got to go. All of that information's already in your box. You're just telling your box turn all the channels on. And they had a lot of problems. This is actually one of the things that OJ was accused of doing. OJ got busted. He did. He got busted for it. Someday I'll tell you the story about someone else that got accused of harnessing this technology. It was not a pleasant experience getting served with papers. The United States of America versus Joseph Gryniuk. Fortunately, I was able to get a good attorney, and it all worked out okay. And I was not doing this illegally. I've been a paid subscriber for DirecTV consistently for the past, but I know how it's done. You know how I know it's done? I teach freaking electronics for a living. And what are they going to beam from the satellite? Packets of information. What's the typical protocol? Hexadecimal. I mean, it's not like they're doing anything crazy. Digital systems are all built on its progression. That's the power of this lecture. The power of this lecture. If you understand what we're talking about here, this is the language machines communicate in. We're not going to pull any surprises on you. One last thing that I want to point out, again, it's not in your book. You see, we got binary, decimal, hexadecimal. There's another one in here called octal. Octal used to be my friend. The first computer, I get emotional. My very first computer.